Today I also discuss one important topic related to measure theory, especially in LP space. Okay, we're also going to discussion about that. Yeah, essentially bounded function or essential bounded function. Okay, let X a mu be a measure space and E belongs to this algebra. Then there exists a measurable function f is said to be essentially bounded if there exists constant m greater than equal to 0 such that mod f less than equal to m mu almost everywhere on E. That is mu x belongs to E if x greater than m equal to 0. Okay, then here gamma infinity f equal to infimum of m greater than equal to 0 mod f less than equal to a mu almost everywhere on E, and this will be called the essential bound of f. Okay, so we also discuss this essential bounded function. This one is what? Just a measure space and some measurable function is said to be essential bounded if measure of, that means this functions greater than m, that means this bound m and this functions greater than m, this set's measure is 0. Okay, then we talk about that this bound of f m is denoted it gamma infinity is infimum of those m's. Okay, and this will be called essential bound of f. Okay, so this one we discussed today. Now we're going to discussion of, obviously we learned another important theorem in previous class. We also discussed now. This one is that means too easy. F is bounded means f less than equal to m. M is the that means m is the upper bound for f, and obviously we talk about this one. F is essentially bounded when the measure of any set, measure of those set x belongs to E such that f x greater than m. Okay, f x greater than m equal to 0. Okay, and we talk about this functions gamma infinity f equal to infimum of those m greater than equal to 0 such that mod f less than equal to a mu almost everywhere on E. Okay, then this one obviously called essential bound of f. Now we also going to discussion of another portion. This portion is the theorem. Okay, theorem, we write this theorem at first. Okay, let phi belongs to 1 infinity. Okay, with conjugate exponent. With conjugate exponent means conjugate exponent q. Okay, that means 1 by p plus 1 by q equal to 1. This condition hold. Okay, then we called pq are conjugate exponent of each other. Okay, so we erase that portion and going to further discussion of that. That means let this x algebra mu be a measure space. Okay, be a measure space. Then what happened? Then we add this one, this lpx equal to lpx this algebra mu. Okay, be a Banach space, be a Banach space with norm what? With norm equal to norm f. Okay, equal to integration of x mod f whole to the power p, here d mu whole to the power 1 by p. Okay, a belongs to LPX. Then what happened? That means then obviously we talk about that. We erase our portion and going to further discussion of that. Okay, we erase our portion and going to further discussion of that. Let here G belongs to LQX. G belongs to LQX and define T LPX to K. Okay, by what? TF equal to integration of x fg d mu. Okay, fg d mu for all f belongs to LPX, for all f belongs to LPX. Okay, then what happened? Then first one, t is a bounded linear function. T is a bounded linear functional and v norm of t equal to norm of c. Okay, so we also discussed in previous, that means in previous class, but we just write this statement. This statement obviously shows that the f belongs to LPX and g belongs to LQX. Then what happened? Then TF equal to integration of a to fg d mu with respect to domain x, and for all f belongs to LPX. Then what happened? Then t is a bounded linear functional and norm t equal to norm g. Okay, now linearity and boundedness is occur. Okay, so here we construct one. That means if we see this boundedness property, that means norm t greater than equal to norm t greater than equal to norm g. This portions handled by so easily if we, that means if we take f equal to here g to the power mod g to the power q minus 1 sin g. Okay, in this way we also discuss here. Okay, in this way we also discuss here, and obviously we done this one, but today we also talk about those portions again. Okay, so we erase that portion and going to further discussion of that. Those portions is what we write it now. Integration of x mod of f whole to the power p d mu equal to what? Integration of x f g whole to the power f to the power p means we know about that, mod g whole to the power p q minus 1, and here s g and g whole to the power mod of this whole to the power p d mu. Okay, this equal to what? Integration of x mod g whole to the power q d mu. Okay, and then this equal to less than plus infinity. Okay, because 1 by p 1 by q, then this one equal to q. Okay, we know about that 1 by p plus 1 by q equal to 1, this one equal to 1 by p equal to 1 by 1 minus q, then q here q minus 1, this implies p multiplied by q minus 1 equal to q. Okay, then we also discuss this one, this portion here. F is p integral. Okay, that means f belongs to LPX. Okay, now we're also going to further discussion of that. Okay, norm f equal to what? Norm f equal to integration of x norm of AP, okay, d mu whole to the power 1 by p. Then what happened? Then we also think about that this one equal to here integration of x g to the power q d mu whole to the power 1 by p. Okay, then this one equal to norm of g to the power q by p. Okay, then this one equal to what? This one equal to norm of g to the power q minus 1. Okay, then what happened? Again we also talk about that norm f equal to this. Now define f0 equal to f by norm of g whole to the power q minus 1. Okay, then this one equal to what? This one equal to g to the mod g whole to the power q minus 1 sine of g divided by norm c whole to the power q minus 1. Okay, then again we erase that portion and going to further discussion of that. Okay, we erase that portion and going to further discussion of that. What happened? Note that here norm of f0 equal to 1 and norm of t equal to, we know about that supremum of f belongs to LPX. Here mod f equal to 1 and here mod of tf. Okay, this greater than equal to t of f0. Mod of t f0 equal to what? Equal to integration of x mod of g whole to the power q minus 1 is g and g. Okay, divided by norm of g whole to the power q minus 1 here g d mu. Okay, here g d mu equal to what? Equal to this one equal to integration of x mod of g whole to the power q by norm of g whole to the power q minus 1 d mu. Okay, g sin g equal to mod g. Okay, so this one happen. We write it now in this way: g sin g equal to mod g. Okay, we also discuss in our that previous class, but we also talk about now because this one is obviously a tough problem. Okay, so if you more discuss this one, then this one is too easy. Okay, is too easily we handle this one. So for this one is mod g whole to the power q minus 1 integration of e mod of g whole to the power q du mu. Okay, then what happened? This one equal to 1 by norm of g whole to the power q minus 1 multiplied by here norm g whole to the power q equal to norm of g. Okay, then what happened? Then norm of t equal to norm of g. Okay, obviously we know about that this one. Okay, so what we get here, get this one, and obviously in previous way we also discussed too easily mod of t less than equal to, so this one happen. Okay, so our that means our necessity condition is done. Now we're going to further discussion of another portion. Okay, we erase that portion. In this way we also discuss this rating theorem. Okay, where we discuss this one, that means this t is linear bounded functional and norm t equal to norm g. Okay, now we write here another portion of this. Let x this algebra mu. Okay, be measure space, be a measure space, be a measure space, and E belongs to this algebra. Okay, then L infinity E equal to the set of all essential bounds, the set of all essential essential bound essential bounded measurable function. Okay, essential bounded measurable function. Okay, then what happened? Then L infinity E equal to be a linear space, okay, over K, be a linear space over K. Okay, then what happened? Then we talk about that for A belongs to L infinity E. Okay, A belongs to L infinity E. Define n infinity F equal to what? Equal to here, equal to infimum of this one. M belongs to 0 plus infinity. Okay, such that mod F less than equal to M, mu almost everywhere on E. Okay, then note that okay, n alpha F plus G less than equal to n alpha F plus n infinity F n infinity G, sorry, n infinity F equal to this one, and then n infinity F equal to this one. Okay, and again n infinity F equal to, sorry, alpha F equal to mod of alpha n infinity F. Okay, alpha belongs to R. Okay, then what, or K, alpha belongs to any field K. Then what happened? Then we talk about that N infinity be a semi-norm on L infinity E. Then N infinity be a semi-norm in L infinity E. Hence N infinity be a semi-norm, okay, semi-norm on L infinity E. Okay, so now we talk about that. We also talk about these portions LPX, this algebra mu equal to what? Equal to measurable space of, that means here Banach space, okay, collection of all equivalence class of elements of LPE. Okay, this one is Banach space of, okay, this one is Banach space, okay, and collection of all equivalence classes, collection of all equivalence classes, okay, of 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 elements of LP, of elements of LPX with norm of FP equal to integration of x f to the power p whole to the power 1 by p. Okay, then this one is Banach space and the collection of all equivalence classes of elements of LPX with norm fp equal to this. Okay, and now L infinity x a mu equal to what? Equal to, we known about that Banach space. This one is Banach space. Okay, collection of all equivalence classes of elements 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 of L infinity x with norm f infinity. Okay, this one is the, that means require conditions, and we erase that portion and going to further discussion of that. Okay, now we write theorem here. Okay, let p equal to 1 and mu is sigma finite. Okay, p equal to 1 and c belongs to L infinity x. Okay, and mu be sigma finite, then what happened? Mu be sigma finite. Okay, then t defined by t belongs to b of L1 x k. Okay, and tf equal to integration of x fg d mu. Okay, where f belongs to Lx. Okay, is bounded linear functional. Is bounded linear functional with norm t equal to norm g. Okay, that means let p equal to 1 and g belongs to L infinity x. Okay, then what happened? Then this one, then t is defined by t equal belongs to b of L1 xk, then tf equal to integration of x fg d mu is bounded linear functions with t norm t equal to g. Okay, we also talk about this portion in previous, and now another theorem. Okay, we write it in a, that means in a better way. Okay, that means we also discuss this class and we write it in better way. Now another theorem, we call it race representation theorem, I think. Okay, okay, then we write it here. Let x, this algebra mu, be a finite measure space, be a finite measure space. Okay, and let p belongs to this 1 infinity with conjugate exponent q, with conjugate exponent q. Okay, then for each bounded function we erase our portion and going to discussion about that. Then for each bounded linear functional, then for each bounded linear functional, okay, t here lpx to k. Okay, there exists unique g belongs to lqx such that here tf equal to integration of x fg d mu. Okay, for all f belongs to lpx. Okay, with with this one, norm t equal to norm g. Okay, then we also discuss this one, this series representation theorem. And now we also going to discussion of another portion. We erase that portion. This one obviously same thing, we written it in another way, and we also erase that portion and going to discussion of another portion. Here, bounded linear operator. Okay, we write it now, bounded linear operator, bounded linear operator. Okay, let x and y be Banach space, y be Banach spaces, and let t x to y be a bounded linear operator, be a bounded linear operator, and let there exist n equal to 1 to infinity xn be series of elements, be series of elements of x such that n equal to 1 to infinity. Okay, xn equal to x belongs to this x. Okay, then what happened, then we talk about that t of n equal to 1 to infinity xn equal to t of limit m tending to infinity n equal to 1 to m, okay, xn, and this one equal to limit m tending to infinity, okay, t of n equal to 1 to m xn. Okay, then what happened, then this one equal to summation n equal to 1 to infinity t of xn. Okay, so this one is the bounded linear operator. xy be Banach spaces and t be a bounded linear operator. Let xn be a series of elements of x such that this one equal to this, then this one equal to this points. Okay, not a problem at all. Okay, so today we stop here. If you get this type of video, please subscribe my channel. If you have gives like, please if you have any questions, suggestions, and any that means any comments, write it in comment box. So today I stop here. Please subscribe my channel and please give like. Okay, so I stop today.